RNA is believed to be the first genetic unit of life. Montmorillonite, as you see here on the board, the structure, Montmorillonite clay is believed to be a catalyst of organic reactions like the formation of RNA nucleotides. This implies that Montmorillonite may have catalyzed some of the reactions on primitive Earth. An experiment was conducted by James Ferris to measure the kinetics of Montmorillonite. Kinetics show that Montmorillonite speeds up the RNA nucleotide formation 100 to 1,000 times more than that of the hydrolysis of imidazole activating groups. Imidazole activating groups act as a leading group in the formation of RNA nucleotide. The results of the experiment signified that Montmorillonite could have been a catalyst for the formation of RNA, the first genetic unit of life.
The RNA world hypothesis states that before there was DNA, RNA was first used to store genetic information. The evidence behind this that supports this hypothesis is RNA's ability to both store genetic information and catalyze chemical reactions. The biggest piece of evidence behind this hypothesis is the fact that ribosomes is a ribozymes, which means that in primitive Earth, RNA was catalyzing chemical reactions before protein was. There's also evidence that DNA came later. For instance, in the cell, deoxyribose is made from ribose sugars. What is believed to have happened is that although RNA was first, DNA was the more stable molecule, which is why now it's used to store genetic information.
LUCA. LUCA means the last universal common ancestor. LUCA most likely was a single-celled organism that lived between 3 and 4 billion years ago. Specialists believe that the two earliest forms of domains were the bacteria and the archaea, with eukarya emerging later on. Dr. Martin and his colleagues did an experiment and saw that 355 genes met the criteria for having connections towards LUCA. Genes adapt to their environments, which made a significant finding that the 355 genes pointed precisely to an organism that met the condition to live in a deep-sea vent. LUCA may have been dependent on hydrogen and metal fibers in a deep-sea vent environment for the origin of life, in which we have displayed here with the branching diagram.
Deep-sea vent theory suggests that life may have begun at submarine hydrothermal vents, spewing key hydrogen-rich molecules. Even now, these vents, rich in chemical and thermal energy, sustain vibrant ecosystems. At the time of life's origin, the early ocean was acidic and filled with positively charged protons, while the deep sea vents spewed out bitter alkaline fluid, which is rich in negatively charged hydroxide ions. It's kind of like a battery in a way. That battery then powered the chemical transformation of carbon dioxide and hydrogen into simple carbon-based molecules such as amino acids or proteins. Eventually, that gradient drove the creation of cellular membranes, complicated proteins, and ribonucleic acids, a molecule that's similar to DNA. There are several hypotheses that can be tested in the present day for submarine hydrothermal vents, such as heat from ridge crest magmatic activity was a primary heat energy source for abiotic synthesis of amino acids. Suitable conditions for each of these reactions were provided by the many different gradients and large surface areas characteristic of submarine hydrothermal vents.